Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up, and don't forget to subscribe. We will see you in the next video, and thank you for watching.
Our lesson today deals with the works of two renowned scientists, Robert Boyle and Jacques Charles, and the laws they have formulated based on their investigations of gases. What we first of all be looking at is pressure in an open container. Then we will investigate Boyle's law, followed by Charles's law, and then we talk a little bit about the Kelvin temperature scale. Here we are having an open system, an open can here, and we just want to talk about what type of pressure the inside of the can will experience versus that outside. But because it is an open can, the pressure inside is having the same effect on the inner walls of the container as the pressure outside. So we're saying two things are happening here. Atmospheric pressure is pushing on the outside, but also the same atmospheric pressure is pushing on the inside of a can. So the general point that can be made is that if you have an open container, the pressure inside will always be same as that outside. So now let's see what happens when we are having a closed container. Here we are having two scenarios. In container A, we have 10 particles, or a certain number of moles of particles, that occupy a volume of 1 liter, and the pressure there was recorded to be 110.0 kilopascals. Before I ask the other question, I just want to ask you this question. This is a plunger here, and we've sealed off the bottom here, so no air can escape. What would one experience if they were to push down on that plunger? Mind you, there's air inside here. If you said that you will experience a pressure on your hand or fingers, then you're correct. As you squeeze a number of gas particles in a smaller volume, the pressure of the gas increases because you're squishing the same number of particles into a smaller surface area there. Therefore, the force per unit surface area will be greater. What do you think will happen in this case? This here has an initial pressure of 110 kilopascals. What do you think this will be, higher or lower? Of course, it was going to be higher, so if you said higher, then you're perfect. So in this case, we have 0.5 liters, and you can see the measured pressure will be equal to 220 kilopascals. Here, when the gas is in a larger volume, we can say the pressure is lower than when the gas is squeezed into a smaller volume. Okay, so you can see a relationship here between volume and pressure here and volume and pressure here. This table here shows the result of what happened when a series of experiments were conducted to show the relationship between the volume and pressure of a fixed mass of gas at constant temperature. Why do we need constant temperature? Because we wanted to investigate the relationships between two variables, pressure and volume. The temperature of the gas constant, because temperature by itself also can affect the pressure as well as volume of the gas. So we want to keep that out of the equation. So let's look at this table here and try to analyze it a little bit. Okay. Let us say that this here was a syringe, okay, in which this experiment was conducted. Initially, the pressure was read to be 100 kilopascals. This here is this sphygmo manometer. It's an instrument that's used for measuring the pressure of gases. It's something similar to your blood pressure kit. So initially, the pressure of that volume of gas inside there was read to be 100 kilopascals, and its volume 1 liter. If I push the plunger down, plunger is coming in this direction, and the pressure is read off, this is what is gotten here, this one here. We now get this value here for the pressure, call it P2. And now, if you look at the volume now, you'll see that the volume is less than what it started with. So the same thing is done again for all these other experiments. So we will say the initial volume was V1, and then the pressure that was obtained from that experiment was P1. In the second experiment now, remember we push the plunger down and we get a second pressure P2 and a different volume V2, okay? In every experiment that was performed, if we multiply the volume by its pressure, we get some values there in every case. These are the values that are obtained by multiplying these values here, okay? Now, if you neglect the small differences there, small differences is not major differences, it can be seen that for a fixed mass of gas at a constant temperature, the product of its volume and pressure for the various experiments is constant. So, neglecting these small differences that you see in a 0.6 there and a 0.6 there, okay, we can safely say that when you multiply the volume and the pressure in each case, the product there is a constant. So Robert Boyle was the first scientist to discover the relationship between the volume and pressure of a fixed mass of gas at a constant temperature. He concluded that the volume of a fixed mass of gas at a constant temperature is inversely proportional to its pressure. So you can formulate an equation here. You can say V is inversely proportional to pressure, because you found there as you increase the pressure, the volume got less. So based on this equation here, we can say that P times V is equal to a constant, and we found that constant in this experiment here, that P times V was equal to this. So if you look at it generally speaking now, we can say that P1 times V1 is equal to P2 times V2. So that's another way of expressing Boyle's law, because this is a constant, right? So if it took the results from experiment 1, where you're having its pressure and volume getting multiplied, you find that you get this value here. For the second experiment, you'll end up with this. So this is P1 times V1. And since these, we said, neglecting that small difference there, we can say that this guy is equal to that guy there. We can generally now say that P1 times V1 is equal to P2 V2. And this is another way of expressing Boyle's law. Okay? Now, how does this equation help us? It helps us to calculate one entity if 3 of them are given. For example, look at this problem here. What pressure must be applied to 2 liters of gas at 100 kilopascals? Change its volume to 0.800 liter. So they're asking you about the pressure, okay? So what are given to us? You have an initial volume here, and you have an initial pressure. So you call this V1, and that is V2. Now you want to change its volume to this. So we call this V2. So what you need now is what? What pressure must be applied to it? You need P2. That's what you do. How do you get P2? Look at this equation here. How do you get this P2? Make P2 the subject of the equation. I taught you how to do that already. Leave these as they are, and you bring down V2 there, okay? And that's how you make P2 the subject of the equation. So in solving that, this is what we have. we'll have that P2 is equal to P1 V1 over V2. And when you insert those values inside there, for P1 and V1 and V2 here, you get this kilopascals, 2.50 times 10 to the power of 2 kilopascals. Next, you're asked to find the final volume. So you're asked to find what? So what is that? V1 or V2? That's V2. That's the initial volume, all right? And that's the initial pressure. And it is pressurized to this amount. So you're looking for V2. You're given V1, P1, and P2. You're provided these, see, V1, P1, and P2. Now what we need? We need to make V2 the subject of the equation. V2 is over here. So you leave these as they are, and you bring down P2 there, and that's how you'll find for V2. Insert those values there, and you can see you have P1 there, V1, that's P2. You can see all these units will cancel out there. Kilopascal is going to go, kilopascal is going to go, and you're left with liters there, and that's what you have there. That's how you use Boyle's law to calculate one of the something that you're asked about, either pressure or volume, if you're given three others. So it's a summary here of Boyle's law. P1 V1 equals P2 V2. P1, you want to know what P1 is? Leave these guys as they are, and you bring down V1, okay? You want to know what V1 is? Leave these as they are, and you bring down P1 there. You want to know what V2 is? Leave these as they are now, and you bring down P2 there, and of course P2 will be equal to P1 V1 over V2 there. And that concludes Boyle's law, which states that the volume of a gas is inversely proportional to its pressure. As you pressurize a gas, okay, its volume gets lesser and lesser. All right, so these are some questions there for you to do. Solutions are in the manual, solutions manual. Now we come to Charles's law. Charles investigated how temperature changes affected the volume of a fixed mass of gas kept at constant pressure. You have a volume of a gas, but you're maintaining that gas at constant pressure, and you want to see how changes in temperature affects it. This is what he did. In a series of experiments, a certain volume of air in a closed syringe with a freely movable plunger is subjected to different temperatures. For each different temperature, the new volume of air in the syringe is noted and recorded. So this is the apparatus that you can use here, and we will explain that to you now. Let's say this was a syringe here, okay, with a fixed volume of gas. That's the volume of gas inside there, all right? And you wanted to see how temperature affects that. So this is your plunger here that's movable. First of all, they have a source of heat, which is a Bunsen burner. You have a tripod here with a gauze here, and you get a beaker here that is acting as a water bath. So you fill that with water, and you have a thermometer that's inserted inside the water bath to monitor temperature changes. Here's a stirrer here. So you want to stir the water all the time to make sure its temperature is uniformly distributed, okay, all over the beaker. And inside there now, you have your syringe that is held up by this stand here and a clamp. Of course, everything has a clamp, and this has a clamp, and the beaker is sitting on this gauze here. So the Bunsen burner is furnishing the heat to the water bath, and from the water bath, heat is transferred to the air inside this syringe here, okay? This was going to happen. The Bunsen burner is used to heat up the water bath. The syringe absorbs the heat from the water bath, and its plunger pushes out. As the air inside here is heated, its molecules will gain kinetic energy, and that is going to cause its pressure to rise, and what it does, it pushes the plunger in that direction, as this arrow is showing here, right? By regulating the flame of the Bunsen burner, right, the temperature within the water bath is changed every 5 to 10 degrees up to about 90 degrees. The new volume of air at each new temperature change is noted and tabulated. For example, if the initial temperature of the water bath is at 25 degrees Celsius, The volume of air within the syringe is noted and tabulated. The water in the water bath is subsequently heated to a temperature 5 degrees higher than this, 30 degrees, and maintained at this same temperature for some time to allow the air in the syringe to attain this new temperature. After this, the new volume of the air in the syringe is noted. This process is repeated for several other 5-degree temperature changes. Let's explain why we said that thing is at constant pressure, okay? And why we are experiencing a change in volume when there's a rise in temperature. Before anything happened, this was your syringe and this was the plunger. The atmosphere is acting on the outside of this syringe. That's why we had to do atmospheric pressure. If we didn't do atmospheric pressure, we won't understand what's going on here, right? And because it is now closed, the plunger is not moving in and out, so we safely say that the pressure inside at this point in time is the same as that outside. So the gas molecules here are bombarding against the walls of the container inside here in this closed container now, right? And that is what is creating a pressure on the inside walls of this syringe here. And of course, the atmospheric pressure is creating the pressure on the outside here, right? Okay, so the two pressures are equal now. Let's see what happens when you start to heat. When this thing gets heated up, the air molecule inside here gain more kinetic energy. And because of that greater kinetic energy, they bombard against the inner walls of the syringe and the base of the movable plunger more forcefully. And remember we said P is equal to F, right? Force over area, okay? So if force gets higher, then P gets higher, right? So that will cause the pressure of the air within the syringe to increase to an extent that it is greater than the atmospheric pressure. So the effect is that this plunger here will move outwards. It will move outwards until the new pressure inside there is the same as the atmospheric pressure. Why does the pressure inside becomes equal to atmospheric pressure after a time? Because you're now increasing the volume there. So the net effect is this. When you heat it up, you get an initial increase in pressure, but as the volume increases, the pressure becomes equal to that of the atmosphere at that particular temperature. The net effect is a gain in volume. You get some increase in volume of the gas as the temperature rises. Let's see what we wrote here. As the air particles are heated up in a closed container, their kinetic energy increases. As a result of this, the particles collide against the walls of the container more forcefully, thereby increasing the pressure in the container. The pressure within the syringe now becomes greater than the outside atmospheric pressure. However, because the plunger is freely mobile, it is able to move outwards to negate any increase in pressure within the syringe until the pressure inside it is the same as the outside pressure. The gas is said to be heated at constant pressure because the pressure within the syringe is kept constant by allowing the plunger to move outwards. Okay? That's why you say it as constant pressure. We are not holding that syringe still. If you held the syringe still, then the pressure would mount. There wouldn't be an increase in volume, but the pressure inside would have increased. But we're allowing the plunger to move to negate any increase in pressure. The net result is that there's a small increase in the volume of the air in the cylinder. If the air particles are kept at this constant temperature, the final volume will stay the same and the pressure inside will still be equal to that outside. What happens if you cool it down? The reverse will happen if the temperature of the air in the syringe is lowered. The pressure within the syringe will be reduced and the atmosphere, being at a higher pressure, will push the plunger in, producing a decrease in volume. So that is how temperature affects the volume of a fixed mass of gas at constant pressure. Now we have to talk about the Kelvin scale, all right? Before we talk about the Kelvin scale, you have to look at what happens there in this graph when a plot of temperature changes and increase in volume is made for a few gases. So look what happens. If you start with a certain volume of a gas, that was the volume there. You can get the volume somewhere here, that's the volume. Talking about gas A. And you increase its temperature. You see what's happening? Its volume is increasing. But what happens with gases is this. If you lower the temperature of a real gas below a certain low temperature, it liquefies. So we cannot investigate the volume of a gas below that temperature because we won't be having a gas. It liquefies. But if you wanted to know what the volume would have been, you extrapolate this graph. So you project this graph right back there. And what you'll find is that it will cut this temperature axis here at negative 273 degrees Celsius. Same thing, there's a different gas. Different gases expand differently. So here it is, all right? If you did that, so to know what the volume would have been, you extrapolate, and here what you have. So technically speaking, a gas would have had no volume at negative 273 degrees Celsius. Lord Kelvin decided to make up his own temperature scale. So he ascribed this negative 273 degrees Celsius to 0 Kelvin according to the Kelvin scale. So the Kelvin scale starts at 0 Kelvin, and that is negative 273 degrees Celsius. So if you want to go to 0 degrees Celsius, 0 degrees Celsius will correspond to 273 Kelvin. Those are degrees Kelvin, okay? So here's absolute 0, negative 273 degrees Celsius, but that is equal to 0 Kelvin. Now to go in that direction, we need to add 273. So 0 Celsius corresponds to 273 Kelvin. 50 degrees Celsius, you take 273 and you add 50 degrees to that, and that's what you get for Kelvin, okay? So when you want to change any temperature from Celsius to Kelvin, you will have to add 273 to that, and then you call it Kelvin. If you want to know what 100 Celsius will be, it will be 373 Kelvin. So that's how you make the conversion. Okay? All right. Let's read this. The graphs above show that as the temperature of any gas at constant pressure increases, its volume increases proportionately. The graph also shows that if the lines are extrapolated downwards, they touch a horizontal axis at that temperature there. The same will be observed for different gases. In theory, this will mean that a gas will have 0 volume at negative 273 degrees Celsius. However, in practice, this is not what is obtained. Gases liquefy before they reach that low temperature. All right. This temperature is now called absolute 0, and is the lowest temperature that can be measured. So this Scottish scientist now, Lord Kelvin, decided to create his own scale, which we talk about. All right? All right. Spoken about that already. To convert from Celsius to Kelvin, you add 273. Obviously, now to change from Kelvin back to Celsius, you'll have to minus 273, and they become Celsius. Charles's law. From the graph obtained on the previous page or graphs, it can be concluded what? That the volume of a fixed mass of gas at constant pressure is directly proportional to the temperature. See? Not like Boyle's law where the volume was inversely proportional to pressure. Temperature will increase the volume. So V is directly proportional to T. So we can say that V is equal to KT, right? And this is what you have here. If you take the volume and you divide it by its temperature, but in this case, you have to use, it works only if you use Kelvin temperature. Number of experiments are done where you use different temperatures, this temperature here, that temperature there, that temperature there, that 4 experiments are done with a fixed mass of gas at a constant pressure. Okay, let's see what relationship exists between V and T here so we can know how to arrive at that constant. So we want to change these here to Kelvin. What do? You add 273. So that's the Kelvin there. That's what the temperature is in Kelvin for each of these, okay? At this temperature in Kelvin, this was a volume, 4.00 liters. When you raise the temperature to 70 degrees Celsius, its new temperature in Kelvin is that, look what happened. The volume increased. When you raise it to 100, this is a new volume. When you raise it by 120 to 120 degrees Celsius, add that, you get a new Kelvin temperature, and that is what you get. So you can see, indeed, as the temperature increases, the volume increases like that. How Charles's law can be represented is by this equation here, that K is equal to V over T. Now for the first experiment, let's take V and divide it by its temperature in Kelvin. If you were to take V and divide it by that, you can take a calculator and do that, you'll get this value, and you can see again in this one here, you get that value there, that value there, that value there. What? It's a constant. So this is how Charles's law is represented. Based on his findings, Charles formulated his law, which states that the volume of a fixed mass of gas at constant pressure increases proportionally as its temperature increases. Since this guy here is a constant, all these are constant, okay, V over T here is the same, V2 over T2, V3 over T3, and so on, okay, is a constant. This is another way of expressing it, that V1 over T1 is equal to V2 over T2. Let me show you how you can calculate that there in experiment 1, and that's the value there for experiment 2. Okay, now you can do some problems. Look at this. A balloon is filled with neon gas, so that's V1, and that is T1. You put it in a refrigerator now, of course. What will happen? You put it in a refrigerator. What will happen to the volume? Get bigger or smaller? The volume will get smaller, right? So you're looking for what? You're looking for V2. So you can use this expression there. You'll use this expression here, okay? We know V1, we know T2, and T1. All you do is to make V2 the subject of the equation. Okay, so to show you how, I show you the mathematics here. So you know V1. Now you have to change your temperature to Kelvin. Changing that, we got this. All right? And that is T1 and that's T. Look at the equation here. This is the equation. Which one do you want? You want to make V2 the subject of the equation. And this is what you do. Leave V2 there. Well, you cross multiply, look. You take T2 and you bring it up there and you leave T1 there, okay? So V2 is equal to V1 times T2 over T1. When you sort the values, you get that there. That's the answer. And here now you're going to have some nice questions here for you to do. Okay. All right. Well, I hope that was helpful to you, and see you next time again.